Okay, so we've got a probability question on an iGCSE paper. So it says, when a fair dice is thrown, the probability of scoring 6 is 1 in 6. So pretty straightforward, ordinary six-sided dice. Aaron throws 4 of these six-sided dice, and we've got to work out the probability that he scores 6, so 6 comes up, with at least one of the 4 dice. So, okay, let's have a look at the examiner's remarks. And they're quite negative. They say very few students used this, that the probability of at least 1 6 has got to be the same as 1, so 100%, minus the probability of getting no 6s at all. Now we'll come to that, but most people didn't use that, so we're going to follow along with what most people did. The most common method was to try finding probabilities from a tree diagram and then summing them. This approach was often only partially successful. So very negative remarks here, and it sounds like not many people got the right answer. So what's the problem here? Well, if we think about the tree diagram that you would have to draw for something like this, because there are 4 events, 4 throws of the dice, you would have a very complicated tree diagram indeed. If I try and draw it, you'll see how complicated it gets. And certainly I wouldn't want to start adding fractions onto a tree diagram that looks like this. There just isn't room. So just a bit too complicated to use a standard tree diagram approach. Okay, so what we want to do here is use a combinations approach, and we want to think about, well, what kind of what possibilities are there here? The probability that he scores 6 with at least 1, so this at least is a key term here, means that it might have been that he got a 1, he got 1 6, or it might have been that he got 2 6s, or he might have got 3 6s, or even all 4 of them might have come up 6. So that's all of those are going to be favourable outcomes. And if that was the case, we would have to multiply up all of those different combinations throughout the tree diagram and then divide by the total number of combinations, and then we will get our, or in this case permutations, then we will get our probability. And that's why this is such a difficult thing, because there are so many different options here, so many different possibilities that we have to total. Well, this is independent probability. So the dice, each time it's thrown, it's still going to be out of 6. So there's no memory, if you like, of the previous throw. So if it's independent probability, what we can do is a tree diagram idea, but multiply out by the number of combinations. So our first one is going to be if we had 4, well, we do have 4 throws, and we're just going to have 1 6. So 4 choose 1 will give us the number of ways. Now I could use my factorial method to find 4 choose 1. I'm actually going to choose to do a Pascal's triangle. So Pascal's triangle, we just total up like this. So that 1 add 1 gives 2, and the 1 add 0 gives the 1 here. So 1 add 0, you always have 1 at the ends here. 1 add 2 gives us 3. 2 add 1 is 3. And then if we go down to here, we've got 1 add 3, 4. 3 add 3 is 6. 3 add 1 is 4. And 1 add 0 is 1. So that's going to be our 4 choose row going along here. So the first one is going to be 4 choose 0. The second one is going to be 4 choose 1. So our answer to 4 choose 1 equals 4. There are 4 ways. 4 ways then of scoring 6. And so it's going to be, that's going to give us 4 times just one of those ways of scoring 6. Well, that would be if we had a 6th on the first go, for example, and then we multiply by the fail option, which is going to be 5 6. The complement of 1 6 is going to be 5 6. So that would be 5 6 cubed. That's probably the easiest way to write it. Okay, now the other possibility, or another possibility, would be if we had 4 choose 2, which is going to equal 6. So that's when we have, again, 6 times this sort of possibility. So we would have 2 this time 6's. So we'd have 1, 6 times 1 6th. So I'm going to write that squared. And this would be squared as well, so 5 6 times 5 6. So in terms of the tree diagram, it would be when we're going along like this, 1 6th, 1 6th, then here would be 5 6ths, and here would be 5 6ths. Okay, so we're always thinking in terms of the tree diagram when we're using this method, but really we're not able to fill in the tree diagram, as it were. Okay, so that's given us 4 choose 2. It might be that we get 3 6's, so that would be 4 again. So 4 times 1 6th times 1 6th times 1 6th, so cubed, and then just one fail option, 5 6ths. Okay. And then finally, we might get all 4 of the throws come up as 6. Very unlikely, but could happen. So 4 choose 4. Let me just rewrite that C. That doesn't look very good. Okay. 4 choose 4. Well, 4 choose 4 is obviously 1. And you can see that on my Pascal's triangle. So that's 1 times, this time just 1 6th times 1 6th times 1 6th times 1 6th, and no 5 6ths at all. Now when I total all of these things up, I should get my probability that he scores 6 with at least one of the 4 dice. So all of these options totaled up. So let's do the first one. So we've got now 1 times 5 cubed, so that's going to be 125. So 5 times 5 times 5, 125. Now 6 times 6 cubed, well, that's going to be always in the denominator. In fact, we're going to have the same thing. So we're going to have 6 to the power 4. Well, that's 6 squared times 6 squared, which is 36 times 36. And that's 1296. 1296 then. Okay, that's the first one done. This one's going to be 6 times 1 in the numerator times 5 squared. So 6 times 25. 6 times 25 is 150. So we've got 150 now in the denominator. Now, I've just noticed a mistake. I didn't do 4 times in that one, did I? So I'll just correct that while I'm going on, and I'll do that in a minute. Okay, and in the, so is that right? 6 times 25 is 150. Yes. So 6 to the power 4, again in the denominator, 1296. And now I'm going to come back to this. 4 times 125, nice and easy, is 500. So there we go. Just correct that mistake. 500 then. And what have we got here? 4 times 1 times, just 5. So it's 20 over 1296. And then finally, what have we got? Well, just 1. 1 times 1. So 1 over 1296. So if I total all of this up, that will give me 500 plus 150, that's 650, plus 20, 670, plus 1, 671. Just add it backwards just to check. 21, 171, 671. So 671 in the numerator, and the denominator is 1296. and checking on the calculator, what have I got? So let's just clear that. 671 divided by 1296. It doesn't say that we have to do that, but just out of curiosity, that's 50, we'll call it 51.8%. So it's 51.8%, that's to 1 BP. Okay, so interestingly, if this is correct, it's come to just over 50%. So it is more likely that we're going to get a 6 in those 4 rows than we're not. Now, if you remember from the examiner's remarks, what they said was that most students didn't realise that you could do it sort of negatively. In other words, you could work on the probability that he fails and then calculate the probability that he succeeds. So do it kind of backwards. And the probability that he's failed, we could draw this on our probability tree diagram, would be if we were just going down here. So there's only one way of doing that. Right, so it would be no sixths at all. It would be 5 sixths times 5 sixths times 5 sixths times 5 sixths. So it'd be just one combination. So there's no point us using the combinations method here. We can just go ahead and say if he fails, then it's going to be 5 sixths to the power 4. Okay, what's that going to be? Well, that would be, let's see, 5 raised to the power 4 is obviously going to be 625. So 625 out of 1296. Okay. So 625 is not too far away from 671, so it does look like we're on the right track here. Let's write, therefore, that the possibility that he succeeds has got to be, well, it must be 1, which is 1296 over 1296, so 1296 is the common denominator, minus 625 over 1296, common denominator, and what's that? 1296 divided by 625 is going to be, oops, not divided by, minus 1296 minus 625 gives us our 671. There we go, 671 over 1296, which is also 51.8%. So that's given us a way of checking the result, or if we were pushed for time, it would be the quicker way of solving the problem.